We are on section 9.3, hypothesis tests for a population mean, standard deviation unknown. So if we know the standard deviation of the population, we can calculate the z-score and use it as our test statistic. That's what we did pretty much in section 9.2. If we do not know the standard deviation of the population, but know the standard deviation of the sample, we can use S, that's the standard deviation of the sample, instead of sigma, which is the standard deviation of the population, and calculate what is known as the t statistic. When x bar is the mean of the sample, x bar minus mu divided by s over the square root of n is a t distribution with n minus 1 degrees of freedom. Now, we've talked about n minus 1 degrees of freedom before. I can't remember exactly which chapter it was, but you're going to use that in your calculator again today. Okay? Our calculators can do this without using a table. The beginning of this section talks about you look it up on a table. You don't need to, guys. We can use the t-CDF function, okay? It's kind of like the normal CDF function, but it's t because we're using the standard deviation of our sample mean. So number 1 says, find the p-value for the following values of the test statistic t. Sample size n and alternate hypotheses h sub 1, okay? We are not going to use the table. So the function that we're going to use in our calculator is actually found under second vars, and it's number 6, t-CDF, okay? So in A, and I'm going to work these down here. In A, I have t equals 2.584, n equals 12, and the alternate hypothesis is mu is greater than the mu sub naught. So that is our null hypothesis. Okay, so we have greater than. That's important, guys. So we're going to go over here to our calculator. And clear that real quick. And we're going to go to second vars. And we're needing number 6, which is the t-CDF. Okay, now notice this says it's greater than. All right, so we're going to start with that t value, the 2.584. Our upper value is going to be 1E99, okay, and our degrees of freedom, well, n is 12, so my degrees of freedom will be 11, because it's n minus 1. We're going to paste that in. So that is what my t-CDF looks like. And remember, guys, we're going, okay, t is 2.584, and what are we looking for here? We're looking for our p-value. So we're looking for that shaded part, okay? And I'll draw a picture in just a second. So that gives me an answer of 0.0127. So let's write down what we did. We have T of CDF we're going from 2.584 to 1E99. Our degrees of freedom are 11, and we get 0.12. Whoops, sorry, I forgot a 0, guys. 0.127. Okay, so let's talk about what, and I'm just going to kind of write it up here underneath there, what A has. And so what it did is it said, okay, well, here's T is 2.584. We're looking for P, guys. Okay, so that chunk right there, because it does say greater than. Okay, So we're looking for that right tail there. And we're saying, okay, that p-value is 0.0127. That's that chunk right there. So I can say my p-value equals 0.0127. I'll put that in green. Okay. So let's look at B. B says T equals negative 1.741. I have N equals 21. And I have the alternate hypothesis being mu is less than mu sub naught. Okay, the null. So it's less than the null. So this time we're looking at that left end. So that should mean that my TCDF is going to go from negative 1E99 up to negative 1.741. And my degrees of freedom will be 20. Remember, degrees of freedom are n minus 1. So if I'm looking at my distribution here, what I'm looking at is I have a negative 1.741, and I'm looking for what this is right here because it is less than the null. So I'm going to go over here to my calculator. I'm going to go up. I'm going to copy that. I'm going to edit that a little bit, and I'm going to put negative 1 second E99, comma, we're going to negative 1.741, comma, 20, close parentheses, equals, and I get 0.0485. So therefore my p-value equals 0.0485. Okay. So that means this chunk right here is 0.0485. All right, let's look at C. C says T equals 3.031, N equals 14, and the alternate is mu does not equal the null. Okay? So, we have one value there. We have one T value there. Okay? So I'm going to go ahead and I'm going to make that TCDF. So I know that TCDF is going to be, and I'm just going to go from, since it's positive, I need to start with the 3.031 and go to 1E99, guys, because that's the positive. If this had been negative, if it had been T equals the negative, and it had been not equals, then we would start at the negative 1E99 and go to the negative part. But we're over here on the positive end. So on C, what we're looking at is they're saying, okay, well, here's my T at 3.031, okay? Now, they want this and this, both the left and the right, okay? So, but since they gave me 3.031, they didn't give me the negative, I'm going to use the positive, and I'm going to make that my lower, and then 1E99 my upper. My degrees of freedom are going to be 13. I'm going to put that in the calculator. So I'm going to go up here. I'm going to take this top one, since it has 1E99 already in it, and I've got 3.031. 1E99, we said those degrees of freedom are 13. And that should give me 0.0048. Now, what that means, guys, is this chunk right here is 0.0048. Okay, well, that's the right. So that also means that the left is 0.0048. Because remember, since we're doing a not equals, we've got to look at both the left and the right. Okay, so that means my p-value is going to be 2 times that. So I'm saying 0.0048 times 2, or you can add them together, is going to equal my p-value. And that will equal 0.0096. Okay, and then D says T equals negative 2.584, N equals 31, and that alternate says that mu does not equal the null. Okay. So this is kind of what I was talking about if it had been the negative there. So it is the negative side this time. And I'm going to draw its picture down here, since I don't have a lot of room up there. So what they're saying is this is negative 2.584 right here. We're wanting this amount, but since it does say not equal to, then you're also wanting this chunk right here. Since they gave me the negative 2.584, I'm going to do TCDF, and we're going to say negative 1E99 to negative 2.584. My degrees of freedom will be 30. That's going to give me a left value of, I'm going to pop the second one right here. And we said that was negative 2.584. And that was 30. And that's 0.0074. Okay, that's that left chunk. That means that right chunk will be the same. If this chunk right here is 0.0074, that means this chunk is also 0.0074. Okay, so we have both of those. So times 2 there is going to equal my p-value. And that will equal 0.0148 as my p-value. Okay. Let's look at example 2. Example 2 says, in example 9.15, the sample size was n equals 76, and we observed that the sample mean, x bar, equaled 2.2, and s equaled 6.1. Remember the 6.1, the s, is our standard deviation of our sample mean. We tested the null hypothesis of mu equals 0 versus the alternate hypothesis that mu is greater than 0, and the p-value was 0.0012. Assume that the sample size was 41 instead of 76. Okay, so the sample size n is now, we're going to change n to 41, but that the values of x bar, so the sample mean is still 2.2, and the standard deviation is still 6.1. Okay? We want to find the value of the test statistic, t. Okay, so we're going to have to use our formula that we have there. So I've got t equals, I know that's going to be x bar minus mu all over s divided by the square root of n. So that's going to be 2.2 minus, what is my mu? Is it equal to 0? Yes, that's still the same. Minus 0 all over s, which is 6.1, divided by the square root of n, which is 41. Okay. When I put that in the calculator, and I can put that all in the calculator at one time, I'll show you guys that. 2.2 minus 0 divided by 6.1 divided by the square root of 41. Okay. And that should give me 2.309 for my t value. So I get t equals 2.309. All right, B's pretty nice. It said how many degrees of freedom are there? Well, degrees of freedom equals n minus 1, which in this case is going to be 41 minus 1, which is 40. Can squeeze that in right there. And then C says find the p-value, okay? So we are looking at, it says mu is greater than 0. So I know that mu is greater than 0. So this is going to give me T CDF of, we're going to the right, so that's going to be 2.309, comma 1E99, comma those degrees of freedom are 40. When I put that in the calculator, I should be getting 0.0131. So I have a p-value equal to 0.0131. And then on D, it says, is the evidence against the null hypothesis stronger or weaker than the evidence from the sample of 76? In the sample of 76, we got a p-value. It says our p-value equaled 0.0012. We got a p-value of 0.0131. It says, is the evidence stronger or weaker? It's going to be weaker. It is weaker. The 76 p-value of 0.0012 is smaller, which makes it stronger. Okay. Much like the z-test will give us the p-value using the standard deviation of the population, the t-test will give us the p-value using the test statistic that we find. I should have said not using the test statistic, but using the standard deviation of the sample mean there, okay? So we actually have, what that's saying is we have a t-test just like we do a z-test. Okay, so let's look at number 3. It says in example 9.16, the alternate hypothesis was mu does not equal 3.5, and the p-value for the two-tailed test was p equals 0.0256. What would the p-value be for the alternate hypothesis? Mu is less than 3.5. Okay, so let's see what we've got there. We have, let's see what it's saying. This doesn't really have anything to do with our p-test value, or our t-test there. Okay, so it said the alternate hypothesis was mu did not equal 3.5, and the p-value for the two-tailed test was, okay, so since it's two-tailed, we're getting this chunk plus this chunk added together equaled 0.0256. Those two added together. Well, they each have to be equal there, so I need to know what did each side equal. So if, that's a plus, guys. If the p-value total equaled 0.0256, then the p-value to the left and the p-value to the right would each be half of that. So that's going to be 0.0256 divided by 2, 0.0256 divided by 2. They're going to be equal, guys, because it's normally distributed and it is symmetric. Let's put that is 0.0128. And so that, of course, is going to give me 0.0128. So we are looking for less than 3.5, which gives me, doesn't really matter, but it is the left value, and we should be getting 0.0128. Okay. Example 4 has us reading a t-test here. Okay. So it says, what are the null and alternate hypotheses? Well, we've got mu is less than 7, so that means that our null hypothesis is 0 equals 7. And my alternate hypothesis is mu is greater than 7. Or less than 7, I'm sorry. It would help if I read the printout correctly. It asks what the sample size is. Well, that's n, so n equals 6. Okay, how many degrees of freedom are there? Well, I know that my degrees of freedom equals n minus 1. So 6 minus 1 is going to give me 5. Okay, what is the value of x bar? We can read that there. X bar is going to equal 6.68. What is the value of S? Remember, that is the standard deviation of my sample mean. In this case, on the TI-84, it's listed as SX, which is 0.205. Okay. What is the value of the test statistic? Make sure you write that out completely. Since they did print that out, they do like you to write that out completely, which gives me negative 3.823, 593, 745. What is the p-value? Once again, you'll need to write that out, 0.006, 16394. And it says, do you reject the null hypothesis at the 0.01 level? Yes, we do, because my p-value is less than the 0.01. Okay, number 5 says, refer to the display in example 4. If the sample mean were 6.80 instead of 6.68, what would the p-value be? If you use the table, we're not going to use a table, guys. So let's see. It says if the sample mean were 6.8, so that means x bar now equals 6.8. We're looking for the p-value. Everything else is staying the same. So that means that mu is 7. And we are looking for mu is less than 7. Okay, I do have n equals 6 still, yes. My degrees of freedom would then be 5. Okay, and our standard deviation will be the same. It didn't say it differed. So we're going to go to I'm going to write this out, and then we'll go over and do it in the calculator. So in the calculator, we're going to go to Stat, and we're going to go to Tests, and we're going to pick 2 this time, a t-test. Okay, our input, once again, is going to be stats. Our null hypothesis will be 7. We can go ahead and enter that sample mean of 6.8. That sampled standard deviation of 0.205. N, of course, is 6. And we will also choose less than the null. Okay? So we're going to go over here to our calculator. I'm just going to clear that. I kind of got a lot going on there. I'm going to go to Stat. I'm going to go over to Tests. I'm going to pick number 2, the t-test. I am on Stats right there. My null is 7. My x-bar is 6.80. My standard deviation is 0.205. N is 6. We're doing less than. And we can calculate that. And we get a p-value of 0.0312. Okay. When we find the critical value, or z-score, using inverse norm, we are using sigma, the standard deviation of the population. If we need the critical value and do not know sigma, we can use inverse t. Okay? So that's a way of, the inverse t is a way of finding the z-score, given the sample standard deviation. Okay? So number 6 says find the critical value or values of the following values of the significance level alpha, sample size n, and alternate hypothesis h sub 1. So we are going to go to second vars, and I'm just going to write this out here in just a second. We're going to second vars and the inverse norm. So I'm going to clear this. I'm going to go to second vars, number 4, inverse t, not inverse norm. My apologies there. What's my area there? Well, that's my alpha. That is 0.05. Okay, my degrees of freedom, it told me n equals 3, so my degrees of freedom is going to be 2. And this is telling me it is greater than 0, greater than the null. Okay. So here's what we've got right here. So we put in inverse t, and we put in 0.05 and 2. And we got back a negative 2.920. Now let's think about what we're getting back. We're getting back a critical value, which is used to, if we knew the standard deviation of the population, this was our z-score. So in essence, you're getting a negative 2.920 z-score, okay? So if it's a negative, then that means it's on the left, guys. Oops, we need to redraw that. Okay, so you're getting something like right here. This is negative 2.920. But our problem says that we want it greater than, not less than. So we don't want it to the left, we want it to the right. So this means that that critical value should be here on the right at positive 2.920. Okay, so our critical value should equal the positive 2.920 because we wanted the right value. Because we had mu is greater than the null. So that means we wanted the right tail. Okay, so let's look at B. B says alpha equals 0.01, n equals 26, and this time it's not equal to. So we need two tails. We need both tails, which means we're going to have two critical values. So I've got inverse t. We're looking at 0.01, and my degrees of freedom will be 25 because n is 26. Well, when I put this in the calculator, let's go up here. I'm going to pick that one again. 1, and my degrees of freedom was... Oh, guys, hold on a minute. Okay, so we need to go back and look at this. It caught me this time. So if I have that alpha is 0.01 and n equals 26, and here's where it got me, because I have mu does not equal the null. Okay, so what is that saying? I should have drawn the picture first. What do I have here? We're saying that this chunk, since it's both, and this chunk, together, these two are 0.01, okay? So if alpha is 0.01, what's alpha over 2? Well, that's 0.01 over 2, which winds up giving me 0.005. Each one of these chunks right here is 0.005 because it's split. Okay? So that means I'm actually finding the inverse t of 0.005, comma 25. Okay? Now, remember, this is just going to give me one of them. If it's the negative, it's the left. So I'm going to go over here. I need to change this to 0.5, comma, what did we say, 25 degrees of freedom? And I get negative 2.7874. Okay, negative 2.7874. Well, that's the left critical value. That's this one, negative 2.7874. So what's the right side one going to be? Well, that's going to be negative. That's going to be a positive 2.7874. So my critical values will equal negative 2.7874 and positive 2.7874. You don't need that positive in front of it. I just made the positive there because I accidentally wrote a negative to start with. Okay, C has alpha equals 0.10. And what else do I have? N equals 81. And our alternate hypothesis is that mu is less than the null hypothesis. So this is a left side, okay? That's going to give me, this one's pretty much straightforward, right? So I'm going to do an inverse t of 0.10, and n is 80. And we're looking for the left, so it should be negative. So if I go back up here, I'm going to pick that first one. Whoops. Let me just clear that. Okay, I'm going to pick, nope, I'm going to clear all of these. Ooh, I got a little mess there going on, don't I? Okay, if I go here and I'm at 10, my degrees of freedom are 80. And that gives me negative 1.2922 as my critical value. If you check that in the book is wrong. It gives the positive, and we are looking at the left side here, so it should be the negative. There have been a couple of times in a different class that uses Alex where there's been a wrong sign in the textbook, and that is what has happened on this one also. So that critical value is at negative 1.2922. D, I have alpha equals 0.05, n equals 14. And this time, that alternate hypothesis is mu does not equal the null, okay? So don't let it trick us this time. So what am I really looking at here? I'm saying that this chunk and this chunk, these two together equal 0.05. So that means I need to find out what alpha over 2 is. And that is going to be 0.025. Okay? So I'm going to do an inverse t of 0.025, comma, degrees of freedom are 13. When I put that in the calculator, I do get negative 2.1604. So that's my left. That's the left, which means, since it is symmetrical, that the right is going to be a positive 2.1604. Okay, and those are going to be my critical values. Okay. All right. Another way to express information about mu is through a confidence interval. If the 95% confidence interval contains the null, then, or mu sub 0, then the null hypothesis will not be rejected at the 0.05 level. Okay, so guys, what we've been looking at is when we have those p-values and we go, okay, well, if it is less than 0.05, then it's lying in that shaded area, so then we reject that null hypothesis. Okay, so the confidence interval is kind of the opposite of that. It's like, okay, we're not shading 0.05, so what's that other chunk over there? Well, that's 0.95, but that's 95% confidence interval. So if that null falls in the confidence interval, then we will not reject it because we're 95% confident that that null is in that interval. So if the 95% confidence interval does not contain mu sub 0, then the null hypothesis will be rejected. So because it's lying out there in that 0.05 level. okay? So a confidence interval contains all the values that are plausible at a particular level. The p-value method is used. When it's used, a hypothesis test tells us precisely how plausible a particular value is, okay? And that's just kind of a definition between what a confidence interval does and what a p-value does, the p-value method. Guys, I looked through your homework. There are no questions over this on your homework, so we just kind of finish up 7, 8, and 8 here, and we have a little bit more. But like I said, I don't think 7, 8, or 9 are on your homework. Okay? So a 95% confidence interval for mu is computed to be 1.75 to 3.25. For each of the following hypotheses, state whether the null hypothesis will be rejected at the 0.05 level. So mu equals 3. Okay, well, does 3 fall in that interval of 1.75 to 3.25? It does. So will the null be rejected? No, it won't. No. Whoops. No. 3. Mu equals 3 falls in the confidence interval (1.75 to 3.25). Okay. What about mu equals 4? Yes, it will be rejected. Okay. Because the mu equals 4 doesn't fall in that interval, so we reject it. How about mu equals 1.7? We're rejecting it. Yes. It will be rejected. Guys, it doesn't fall in that interval. The number has to be between 1.75 and 3.25 for it to be accepted. Otherwise, it is rejected. So if mu equals 3.5 is given, will it be rejected? Yep, it's going to be rejected. Yes, it will be rejected. Okay, 8. You want to test the null hypothesis mu equals 4 versus it doesn't equal 4. So you compute a 95% confidence interval for mu. The 95% confidence interval is 5.1 to 7.2. Do you reject the null hypothesis at the alpha equals 0.05 level? Yes, because 4 doesn't fall between 5.1 and 7.2. Your friend thinks that 0.01 is a more appropriate significance level. Can you tell from the confidence interval whether to reject at this level? No, we cannot tell. Guys, we don't know the confidence interval. We don't know those values with alpha equals 0.01. Okay. The little chart right here, the table 9.2, guys, this is just to remind you what a type 1 error is and a type 2 error. So if we reject the null hypothesis, but it was actually true, that is a type 1 error. That is the most serious type of error that there is. When a test is performed with a significance level alpha, the probability of a type 1 error is alpha. Okay, the smaller a value we choose for the significance level of alpha, the smaller, okay, the second bullet says the smaller a value we choose for the significance level alpha, the smaller the probability of a type 1 error becomes, and the larger the probability of a type 2 error becomes. Okay, so in question 9, we have a hypothesis test is performed at a significance level alpha equals 0.05. What is the probability of a type 1 error? Well, guys, that's just going to be 0.05. Okay? Charlie will perform a hypothesis test at the alpha equals 0.05 level. Felice will perform the same test at the alpha equals 0.01 level. If the null hypothesis is true, who has a greater probability of making a type 1 error? That's going to be Charlie, guys, because he has the higher alpha. His alpha is greater than Felice's. Well, if in B, the null hypothesis is false, who has a greater probability of making a type 2 error? Well, that's going to be Felice. Okay, and that is all about the type 1 and type 2 errors. And that is the end of 9.3.